Hi, my name is Greg Spector, and this is my final project for Duke University's Pratt School of Engineering, Machine Learning Foundations for Product Managers. In this project, I will build a machine learning model that will use 4 independent variables: temperature, exhaust vacuum, ambient pressure, and relative humidity, to predict the expected energy output of a combined cycle power plant. To build this model, I have been provided a set of 9,568 hourly average environmental readings. The project objectives are to determine which machine learning approach best fits the scenario, which set of features should be used in the model, and which algorithm will produce the best outcomes. In order to accomplish this goal, I will manually split my data, compare 2 different models, selecting one that achieves the best results, and evaluate the performance of the final model. My first step is to get a better understanding of the data and the relationship of the variables. To do this, I started by plotting each of the input variables or features against the energy output. There appears to be a strong linear correlation for some of the variables. Based on the data visualization, number of features, and need for interpretability, accuracy, and efficiency, I have selected multiple linear regression. I have excluded lasso and ridge regressions based on the number of variables and complexity. I may choose to return to these methods should multiple linear regression prove inadequate. The data will be split 80-20 between training and test data, respectively. After running a multiple linear regression on the training data consisting of 7,655 observations or rows, I observed that my R-square is 0.9297. This represents the proportion of variability in my dependent variable that can be explained by the independent variables. In other words, how closely the energy output correlates with the environmental readings. The other observation is that ambient pressure correlates the least with the energy output. This will inform my feature selection. For Model A, I've decided to include temperature, exhaust vacuum, and relative humidity, and to exclude ambient pressure from the feature set. For Model B, I have included all features in the feature set: temperature, exhaust vacuum, ambient pressure, and relative humidity. I will use root mean square, mean absolute percentage error, and mean absolute error to validate my models. As you can see, I used Excel to run my linear regressions in this project. Taking a closer look at the results for Model A, I have used 7,655 observations, which represents 80% of my total data set. My R-squared is 0.9294. My RMSE is 4.541. My MAPE is 0.7971. And my MAE is 3.6153. Here are the results for Model B run on the training data as well. Taking a closer look once again, I've used 7,655 observations, which represents, again, 80% of my data. My R-square is 0.9297, which is a slightly higher correlation than Model A. My RMSE is 4.531. MAPE is 0.7970, and my MAE is 3.6160. Comparing the results of the 2 models, we see that Model B has a very slight advantage over Model A. If I were to stop here, I would select Model B as the preferred model and test that model on the testing data. However, due to the small testing difference between the 2 models, due to the small difference between the 2 models, I have decided to run both models on the test data to see if I get the same results. Running Model A on the test data gives me very similar results on the training data. Running Model B on the test data also gives me slightly better but similar results as on the training data. Comparing the two once again, I get consistently small differences between the two models. Having completed this additional step, I would select model B as it gives slightly improved results. However, in a real-world example, I would expect to have information that was not part of this project, which could inform and possibly alter my decision. For example, including more features makes the model more complex and requires more computing power. I would balance the additional cost of computing power against the cost of potential errors that a more simple and efficient but less accurate model such as Model A would create. In summation, absent of the additional information, I would select Model B if accuracy is my only measure of success. Thank you for reviewing my project, and I hope you have a wonderful day.